So in this video lecture, we will be continuing with our previous topic of functions of an aquifer, and in the last topic we had studied about the porosity. So if you don't remember it, let me just show it to you. Porosity is what? It is the ratio of volume of pores that are there, or we call them as volume of interstices, 2 divided by the total volume of the rock. Correct. So now let us study what is specific yield. So specific yield may be defined as the quantity of water that a unit volume of aquifer drains by gravity. So specific yield is volume of water drained under gravity divided by the total volume. Okay, so it is again a ratio as same as compared to the porosity. Porosity was the total interstices, the total volume of interstices or volume of voids divided by total volume. This is volume of water drained under gravity. So what does this mean? That now this volume of voids or volume of voids, some part of this will hold water and some part of it will drain the water. Drain water under gravity. Okay, so some of the voids will hold the water, it won't drain under the gravity, and some part of it, some part of the voids, that is if it is filled with water, then the water can be drained easily under the influence of gravity. So this specific yield is related to that volume of voids in which if the water is stored, it can be easily taken out. A rock may be porous but may not necessarily yield water, for example clay. So as I told you that even in the porous rocks, in some kind of rocks, even if water is stored into it, it is not easily possible to take it out. And the example is you can see in these two cases. In the first scenario, all the interstices are connected to each other, so it is easier to take this out. And in the second one, since the pores are not connected, it is not easier to take the water or to extract water from such rocks. Factors that are commonly responsible to adversely affect the porosity of rock are: first is adhesion to grains. Some groundwater is attached to the surface of grains of rock due to molecular attraction and is not easily available for circulation. So some water that is present inside the rock, it can be attached to the sand grains, or even in the voids it can be attached, and due to the molecular attraction, it won't be easier for that water to drain under gravity. For example, let us consider that this to be a rock, and there is a void here inside. Okay, there are certain voids inside these rocks. I am just magnifying it, and let us say that there is some water that is there inside this pore, but it is adhered to that to the walls of those voids. So because of the molecular attraction or because of some other cohesive forces and other forces, this water may not be drained under the influence of gravity, right? So this will affect the porosity of the rock and subsequently the specific yield as well. Second, unconnected pores. So this is what is shown in these two images, that in this image the pores are not connected to each other properly, and hence it becomes difficult for the liquid to be extracted. So though present in good abundance and even containing some water, such pores are separated from each other, hence the liquid in them cannot circulate. Alright. The next is specific retention. So specific retention is the term used to express the amount of water retained by a unit volume of aquifer after allowing gravity drainage through it. So as I told you previously that volume of voids, this will have two types. First is it will hold water and second, it will allow the drainage. So the water that is remaining in these voids after the drainage has taken place, that volume of water divided by the total volume of rock will give you specific retention. Okay, so specific retention is volume of water retained divided by the total volume, and what was specific yield? It was volume of water which is drained under gravity divided by the total volume. So what we can actually get from this is, if I add specific yield and specific retention, it is volume of water drained under gravity upon total volume plus volume of water retained upon total volume. So if I add these two terms up, I will get volume of interstices, total volume of interstices, because if let us say if there is water in this pore, okay, and after the free drainage, the water in the pore remains only this much. After the free drainage of water, there is some water that is still attached to the pore, but it is present, it is not left the pore. So is it not this volume of the pore is this volume of this water plus volume of the water that had drained? So it becomes the volume of interstices, right? And we have seen this ratio before, volume of interstices upon total volume. It is nothing but porosity. So porosity is summation of specific yield plus specific retention, right? Now let us come to the topic of rocks as aquifers. So the sedimentary rocks that act as good aquifers are gravels, sands, sandstones, limestone and glacial deposits. So let us learn about gravels first. These are classed among the best kind of formations to yield groundwater because they have a lot of porosity to them and they can store the water very easily. Hydraulic conductivity, that is how much water can travel through them, is anywhere between 100 to 1000 meters a day. So it offers a very good hydraulic conductivity. Their porosity may range between 25 to 40%, so a good amount of porosity, and specific yield is between 15 to 30%. So 15 to 30% of that porosity can give you water which can drain out easily under gravity. Sands have hydraulic conductivity of 10 to 100 meters per day, so that much amount of water can travel. And when we talk about this meters, it means that, let us say we have this bed of sand here, okay, and if water is percolating, like if water is coming from here, then the depth that it can travel, the water will travel like this. So the height that it can travel, no matter what the area is, the height that it can travel is 10 to 10 meters or 10 to 100 meters per day. Porosity of 25 to 40% and specific yield of 15 to 25%. In many cases they prove even better than gravels because of their extensive continuity. So since sand have a greater depths as compared to gravels, they are very long as compared to gravels, means in the range criteria they are well spread across a particular area, so they prove to be better in certain cases. Sandstones, so coarse grained sandstone with rather imperfect cement are classed among the excellent aquifers. So this is the coarse grained sandstone, and what do you mean by cement? It means that the binding particles which hold those sediments, we have learned about them as cementitious material. So if that cementitious material is not of a very good quality, it means that the sandstone is going to have more pores into it, and therefore such kind of sandstones are capable of holding good amount of water. The fine grained varieties, this is also a type of sandstone, this is also a type of sandstone, but you can see the difference clearly. This is a much refined one and a much compacted one also, Here you can see there are so many pores, but here it is compacted very to a greater degree, so that compaction part is more. This type of sandstone is it won't store much of the water, therefore it is not as useful an aquifer as the other type. Porosity ranging from 5 to 30% and specific yield from 5 to 15%. Hydraulic conductivity of sandstone is anywhere between 1 to 100 meters per day. Sandstone formations are among the most important groundwater reservoirs all over the world. Talking about the limestones, porosity of limestone varies from 1 to 20%. Hydraulic conductivity is as high as 100 meters per day, or even to be classed among the best one, or the extremely permeable rocks. Next is glacial deposits. So glacial deposits have hydraulic conductivity of 5 to 10,000 meter cube per day. Here we are not talking about how much depth it is traveling, but we are talking about the flow, how much flow glacial deposits can have. So this is the unit of discharge, right? Meter cube per day. So it can be easily converted to meter cube per second, or you have also learned it as cubic. This is for discharge. So here they have given a hydraulic conductivity in terms of discharge. Let us talk about igneous rocks now. Igneous rocks have two types. First is intrusive rocks and second is extrusive rocks. Intrusive rocks also have two types. One which do not act as aquifer because they are dense, closely crystallized, no openings, impermeable. And when intrusive rocks can act as aquifer, they can act as aquifer when cracks traverse through the body of the rocks due to jointing, folding, faulting, etc. So intrusive rocks generally do not form a good aquifer because they have a very dense packed structure and they are very closely crystallized, but they can form aquifer when there are cracks that are forming into it, and this kind of thing we had learned in previous lecture and we called it as aquitard. It is a type of aquifuge in which the cracks have developed, so it can hold the water. Extrusive rocks. Now these rocks have great variation in water bearing capacities. Lavas are generally of two types. Acidic lavas, means we can differentiate them into two as acidic lavas and basic lavas. So what is this? Acidic and basic is, acidic are viscous in nature, that is they have a great viscosity, they are thick, they are light in color and have high silica content. Basic lavas are non-viscous, that is opposite of this acidic lavas. They are non-viscous, they are darker in color, as well as they have less silica content. So depending on this, the types of rock formed are also different. Acidic lavas tend to form a lot of interstices, but these interstices get filled with ash. So when the rocks are formed due to acidic lavas, there are a lot of pores that are available in those rocks, but generally those pores get filled with ash. Basic volcanic rocks are rich in cavities, so they also have a lot of pores, and these are mainly due to the gas escaping from the rocks and cracks formed while cooling of the rock. Thus they form good rock to act as aquifer. So what we can see from extrusive rocks is the basic volcano rocks are more better option for aquifers rather than the acidic one. So metamorphic rocks also have a variation as when compared as aquifer, because the crystalline and the compact type of metamorphic rocks do not form a good aquifer. These rocks include quartzites, marbles, etc. and they are non-porous, impermeable, so that the water cannot enter, neither it can leave, and no prospect for groundwater reserves. Only if there is cracking involved into this, as we saw in the igneous rocks case as well, aquitards, right? Only if fracture is there in the rock, then it can hold water. Metamorphic rocks which are inherently fractured and foliated, such as schists, slates, phyllites, etc., may prove exceptionally good aquifer in broader sense. So you can see the structure of metamorphic rock which is foliated. So this can form a good aquifer since it can hold water into it. So that's it for today's lecture, and in the next lecture we'll be starting with a new topic. Till then, take care. Thank you.